Loops of a wire rotate around this axis. Here is the magnetic flux density, vector B, and this is the normal line of the surface of the loops, vector dA, and the angle between vector B and vector dA is theta. According to Faraday's law, induced EMF equals this, minus d phi B over dt, and phi B is B dot A. A is area of the loops of the surface of the loops, and there are n loops, so times n. A is the surface area of one loop. N is the number of loops over dt. So BA is a constant, and cosine theta is a function of time. The angle theta is omega t. Omega is angular speed. So d cosine omega t over dt is minus sine omega t times omega. So induced EMF is this. As NBA omega is constant, so when sine omega t is 1, Vmax equals this. So V is a function of time, Vmax times sine omega t. And this is the diagram of V of t. This is t, this is period t, and this is Vmax. Let's compare the diagram of phi b with the diagram of V. Phi b is a diagram, a function of t or theta. Theta and t, theta is omega t. So when the angle, when the loops start to rotate, the angle between vector B and vector A is 0. And that is the maximum phi b at time 0. Phi b is BA, and EMF is 0, as the derivative of phi b at time 0 or angle 0 is 0 here. As we know that EMF is minus d phi over dt. So this is opposite to the, it's minus the derivative of this function. But that minus is just a matter of direction of the voltage, but it doesn't affect the magnitude of the voltage. So let's just look at the magnitude and forget about the direction. Okay, here the derivative, the magnitude of the derivative is 0. so the voltage is 0. And the magnitude of the changing rate of phi b is increasing, and it reaches maximum at the angle pi over 2. So this is the maximum voltage. And so the magnitude of the changing rate is decreasing until it reaches angle pi, until the loops rotate to angle pi. The magnitude of changing rate of phi b is 0. So that is EMF 0. So these two diagrams are related with each other.